Hey everyone, today we are going to talk about trig functions of acute angles. This lesson is going to have three parts. First, we're going to define the three basic trig functions using the lengths of the sides of a special right triangle. Next, we're going to use special right triangles to define trig functions of real numbers. And finally, we're going to try and understand the difference between an exact solution and a calculator solution. So let's take a look at this triangle down below. At first, you might be a little bit confused about some of these letters that you see or symbols that you see here. These are Greek letters from the Greek alphabet, and we use those frequently when we're working with trig functions. So the first letter in the Greek alphabet is the Greek letter alpha. So it looks like this. The next letter is the letter beta. And then we have the Greek letter gamma. That one kind of looks like a Y to me. I mean, they kind of all look like familiar letters, but we're going to use them pretty frequently in trigonometry. And you'll see a couple more of these Greek letters as we continue along. So when I'm looking at a right triangle, the very first side that I try and identify is the hypotenuse. The hypotenuse is the side that's directly across from your 90-degree angle. That's this guy right here. You can tell our 90-degree angle because it's usually designated with this little square in the corner. So the hypotenuse, which is the longest side in a right triangle, is directly across from the right angle. That side will always be the hypotenuse. It'll never be anywhere else. So first thing you want to do is identify where your hypotenuse is in your right triangle. Next, you got to figure out which angle that we're dealing with. Are we going to be dealing with alpha? Are we going to be dealing with beta? Which of these angles is the question asking us about? So I'm going to start with angle alpha. Okay? Now there are two other sides that we don't know. We obviously already know our hypotenuse. It's directly across from our right angle. So then what are B and A? What are these sides compared to the angle alpha? Well, the side that is opposite angle alpha is little a. So we call that our opposite side. Now, while there are two sides that make up angle alpha, only one of them is considered the adjacent side. That's going to be angle or side beta. We call this the adjacent side because we know that side C is already the hypotenuse. So we have our hypotenuse, the opposite side, and the leftover one is the adjacent. Now, from these three sides, in terms of angle alpha, we can write three trigonometric functions. So the sine of angle alpha is simply the opposite side length, A, divided by the hypotenuse side length, C. The cosine of angle alpha is the adjacent side. So remember, our adjacent side was B, and the hypotenuse side, C. So it's your adjacent divided by the hypotenuse. Finally, the third basic trig function is called tangent. And tangent of alpha is the ratio that compares the opposite side to the adjacent side. So this would be A divided by B. And these are our three basic trig functions. Let's do some more. So here's another right triangle, triangle ABC. Right away, we've identified that the hypotenuse is directly across from our right angle. The opposite side, so if we're talking about angle A in this case, the opposite side of angle A is little b, and the side that is adjacent to angle A is little a. So your sine is the opposite divided by the hypotenuse. So our opposite side was B, divided by the hypotenuse, which we labeled little c. And we can keep going. Cosine is your adjacent divided by the hypotenuse. So it's going to be the adjacent side, which is side A on this triangle, divided by the hypotenuse, which I have labeled little c. Our tangent doesn't have the hypotenuse at all. It's the opposite divided by the adjacent. So the side that is opposite angle A is little b, and the side that is adjacent to angle A is little a. Usually in trig, or when we're working with triangles, we will label our angles as capital letters and our sides as lowercase letters, just in case you were wondering. So here we go for our first example. Some teachers will teach you something called SOHCAHTOA. It's a mnemonic device to help you remember the order that those trig ratios go in. So, because sine is the opposite over hypotenuse, so because cosine is the adjacent divided by the hypotenuse, and TOA because tangent is the opposite divided by the adjacent. So for our first example here, we're just going to find the value of each of the three basic trig functions from this right triangle. So let's go ahead and find the sine of angle, it's another Greek letter. The Greek letter that looks like this is called theta. Okay, so this is the Greek letter theta. It's probably the most common Greek letter used for angles. If I'm going to find the sine of the Greek letter or the angle theta, I need to find the opposite and the hypotenuse. You might start by finding the hypotenuse first. So there's the hypotenuse. It's directly across from our right angle. Then I like to find my opposite side because that's directly across from the angle I'm working with. And then all that's left over is your adjacent side. There we go. So sine is the opposite over hypotenuse. So that's going to be 8 divided by 17, since our opposite side was 8 and the hypotenuse side was 17. Now we can calculate the cosine of angle theta. Cosine is the adjacent divided by the hypotenuse. So just find my adjacent side. That length was 15. We didn't have any units on this problem. And the hypotenuse is 17. Now, it won't be difficult for us to find tangent, especially since we started off the problem by identifying each of the sides first. Tangent is your opposite divided by the adjacent. So my opposite is 8. That's the side that's opposite angle theta. And the adjacent is 15, because that's the side that's not the hypotenuse side that actually makes the angle. And this is our solution. All three of the basic trig functions from this right triangle. Not too bad, right? So we do have some famous right triangles. The first is called a 45-degree triangle. Now, 45 degrees happens to be the same as pi over 4 radians. So we're going to find all three trig functions for a 45-degree angle. So if this is a triangle, a special right triangle with 45 degrees, it actually has so let's go ahead and label it like we did previously. If this is our angle with 45 degrees, first we want to start off by finding the hypotenuse. Then we want to find the side that is opposite our angle. And then we'll find the adjacent side. Now, the thing that makes this so special is that every 45-degree triangle is going to be in this kind of ratio. The sides, the adjacent side and the opposite side are going to have the same length, and the hypotenuse side is going to be the square root of 2 multiplied by whatever this length is. Always, it has the same proportion. So let's try and find all three of the trig functions for a 45-degree angle. So for the sine of 45, we're going to have our opposite divided by the hypotenuse. Well, the opposite side was 1, and the hypotenuse side was the square root of 2. Now, in the world of math, we like to do what we call rationalizing the denominator. You're not supposed to leave a square root in your denominator. So what you do is you take that square root that is in the denominator and you multiply it on the top and on the bottom. So really it's like a fancy 1, and 1 times the square root of 2 is the square root of 2, and the square root of 2 times the square root of 2 is 2. Easy peasy. It's the only time I'm going to explain that. Now, the cosine of 45. Cosine is your adjacent side divided by the hypotenuse. So my adjacent side is 1, my hypotenuse is the square root of 2. So we've got 1 divided by the square root of 2, and then we have to rationalize it. And there we go. Notice that the sine of 45 degrees and the cosine of 45 degrees are the same. That's what I love about 45-degree angles. Lastly, we've got the tangent of 45. Remember, tangent is the opposite divided by the adjacent. So our opposite was 1 and our adjacent was 1. And of course, 1 divided by 1 is 1. And there you have it, our special right triangle, the 45-degree triangle. But there's another one. We got the 30, 60, 90 triangle. The 30 degrees is the same as pi over 6 radians, and 60 degrees is the same as pi over 3 radians. So these triangles would be the same as we're looking at them. Now, if we're focusing on 30 degrees, so let's focus on 30 degrees here. We still have, no matter what, our hypotenuse is going to be directly across from our right angle. So that's our hypotenuse. But for angle 30 degrees, directly opposite it is going to be a side length of 1. And directly adjacent to it is going to be the square root of 3. Now, every 30, 60, 90 triangle is going to have this relationship in common. Whatever you have directly across from the 30-degree side, if you multiply it by 2, that's going to be the hypotenuse length. And also, whatever the side is directly across from 30 degrees, if you multiply it by the square root of 3, that will give you the adjacent length. Okay? So even if this number isn't a 1, you can grow this triangle out. So now let's go ahead and label the sine, cosine, and tangent of 30 degrees. Remember, sine is our opposite, which is 1, divided by the hypotenuse, which is 2. So obviously 1/2 is just 1/2. Now cosine of 30 degrees is the adjacent side, which was the square root of 3, divided by the hypotenuse, which was 2. We don't need to rationalize the numerator. Square roots in the numerator are perfectly acceptable. Finally, the tangent of 30 degrees is the opposite, which is 1, divided by the adjacent, which is the square root of 3. And this one we do need to rationalize. So we'll multiply the top and bottom by the square root of 3, and we get rad 3 over 3. So let's do the same thing now, but this time we're going to work on 60 degrees. So let's erase what we have here, except I'm going to leave the hypotenuse at 2, because no matter what angle we're working with, the hypotenuse is always going to be directly across from the right angle. So if we're focusing on 60 degrees, what you're going to notice is that your opposite side is now going to be the square root of 3. And the adjacent side is now going to be 1. So that's going to change what our ratios look like over here. The sine of 60 degrees is the opposite, square root of 3, divided by the hypotenuse, which is 2. The cosine is the adjacent, 1, divided by the hypotenuse, 2. And the tangent is the opposite, square root of 3, divided by the adjacent, which is 1. And the square root of 3 divided by 1 is just the square root of 3. You don't have to write it as a fraction if you don't want to. And those are the trig ratios for the special right triangles. So now that we know these special right triangles, we can use them to answer some questions that might have been more difficult for us before. For example, this one asks us to find the acute angle theta that satisfies the given equation. Then they want us to give theta in both degrees and radians, and they don't want you to use a calculator. So here's our two special right triangles. We're looking for the sine of some angle that is equal to 1/2. So I'm trying to figure out what this angle actually is. So where would the sine, remember sine is your opposite divided by your hypotenuse. Which one of these triangles does that look like? Hopefully you went directly to this triangle because this is the only one where your hypotenuse, directly across from your right angle, is actually equal to 2. So that means that the opposite has to be equal to 1. Well, if this is our opposite, and this is the hypotenuse, then the angle we're discussing has to be 30 degrees. So theta must be 30 degrees. It's the only angle that has an opposite of 1 and a hypotenuse of 2. All right, how about with example number 3? We're supposed to find the value of theta from this special right triangle. So instead of having an equation like we had on the last one, now we've got this. Well, what do we notice here? Don't forget, these trig functions are ratios. They're fractions. So the only 2 bits of information I know is the hypotenuse, right? I can tell that because it's directly across from my right angle. And I do know, 4. Is 4 my adjacent side or my opposite side? Hopefully you said adjacent. So I know that cosine of my angle is the adjacent divided by the hypotenuse. So 4/8, that reduces to 1/2. Which one of these angles has a cosine of 1/2? Where cosine is my adjacent over hypotenuse, which one has a hypotenuse of 2? Again, this triangle has a hypotenuse of 2. Which one of these angles is the 1? Well, this guy's got to be the 1, right? Because it's 1. So this is the adjacent side. If this is hypotenuse and this is adjacent, is 1 adjacent to 30 degrees or is it adjacent to 60 degrees? Hopefully you guys can see that it has to be adjacent to 60 degrees. So therefore, theta must be 60 degrees. Next, we're going to try and evaluate this one without a calculator. So here I've got the tangent of pi over 4. So here's our angle. I'm telling you it's pi over 4. Well, I also know that pi over 4 radians is the same as 45 degrees, right? So I've got to be working with this 45-degree triangle here. So adios to this one. Bye. So we're supposed to try and find the tangent of pi over 4. Remember, tangent is the opposite divided by the adjacent. Well, the tangent of pi over 4, or 45-degree angles, is the opposite 1 divided by the adjacent 1. And it doesn't matter which one of the 45-degree side angles that I'm talking about, because the answer is going to be 1. Didn't even need to type it into a calculator. All right, example number 5. Ooh, we are going through these quickly. So we're supposed to determine the value of the 3 basic trig functions on a circle with a radius of 1. We are not supposed to use a calculator. So here we can see where these are located on the unit circle, which has a radius of 1, and they're plotted. So your x comma y is how a point is always written. That's called an ordered pair. And that's going to be your cosine value, comma, your sine value. So your x value goes along with cosine, your y value corresponds to your sine value. So we're given pi over 4. That's the angle we're working with. So all these other ones, I don't need to see them. I only need pi over 4. I'm only interested in pi over 4. So pi over 4 has the point, the square root of 2 over 2, comma, the square root of 2 over 2. Our cosine, and our sine. So the sine of pi over 4 is our y value, the square root of 2 over 2. The cosine of pi over 4 is our x value, the square root of 2 over 2. And the tangent, well, the tangent's a little bit trickier. That's your y value divided by your x value. So my y value was the square root of 2 over 2. And my x value is the square root of 2 over 2. And hopefully you know that any number divided by itself is equal to 1. So tangent is 1. So now let's talk about how you can do this on a calculator. But first, watch out, because you might think that using a calculator is a fast ticket to Easy Town, but it is not. You can make some mistakes. So first of all, you need to make sure that your calculator is in the proper mode. I can't even tell you how many times I have graded a test and I could tell that a student just had their calculator in the wrong mode, and that was what was generating all the wrong answers. It's a silly reason to get a question wrong, so always make sure that your calculator's in the appropriate mode before you begin. Number 2 is another common error, using inverse trig keys for cotangent, secant, and cosecant. The little inverse key is not going to give you those reciprocal trig functions. That's going to give you an inverse, not reciprocal trig. We're going to talk more about reciprocal trig in the future, but just know that this key is not going to give it to you. And then finally, another one, using incorrect shorthand. If you ever need to square one of your trig ratios, you can't just you put your square in on the calculator like this, depending on the calculator, I suppose. Most of them you'll have to write your trig all the way out and then square the result. And finally, don't be sloppy. Close your parentheses on your calculator. It'll start them, but it won't finish them for you, so you have to do it for yourself. These are definitely 4 key things that are going to stop you from getting questions wrong inadvertently on a test or on a homework assignment. So be careful. So the first one I was talking to you about was about being in the wrong mode. So if this is your calculator, most of us have an 84, TI 84. You turn it on, you hit the mode key, and it's going to bring up this menu. So if you're working in radians, you want to make sure that the radians mode is highlighted. If you're in degrees, you want to make sure the degree mode is highlighted. Okay, so here I've got my calculator, got lots of stuff in there. Okay, if I want to put that into degree mode, I'm going to click on mode, and then I have to scroll down. I see right now radian is highlighted, so I'm going to arrow over, and then I have to hit enter to turn it into degrees mode. Now to get out of this menu, I'm going to go second and then mode. That's going to quit me right out. Okay? This one will be our last example. I bet you didn't think it would ever end. So make sure that when you are evaluating a problem that you read the directions carefully, and make sure that if it says to give an exact answer, that you do not bust out that calculator. Okay, so exact answers mean they want you to have your answer with the square root in it. So this question asks us to evaluate without a calculator. That's your first clue not to use a calculator. And then to give an exact answer. That's your second clue not to use your calculator. So it's asking us, what's the sine of 45? Now, as you hopefully recall from our special right triangles, 45-degree angles, my very favorite angle, have legs that have a length of 1 and have a hypotenuse that is the square root of 2. Next, we're going to calculate the sine. Remember, the sine is your opposite divided by the hypotenuse. So the opposite side here from angle 45 is 1, and your hypotenuse is the square root of 2. Of course, we're going to rationalize this denominator, and that's going to give me the square root of 2 over 2. That is my exact answer. It's perfect. There is no rounding happening at all. And finally, how do we do this thing on a calculator? Why have I shown you how to do all this stuff and taught you all the modes and everything of a calculator if I'm not going to have you use it? Well, now it's time to use it. So we are going to evaluate the sine of 45 on our calculator. Let's remember, this is the sine of 45 degrees. So double check, even though we just did, we're going to go to mode, and I'm going to make sure that my calculator highlights degrees. Believe me when I tell you, it's worth the time to spend to actually put that in there and double check it. So we're going to find the sine key and click that. We're going to put in 45, and I'm not going to be lazy. I'm going to close my parentheses and hit enter. And this gives me a nice pretty little solution here. And it's asking me to round this to 3 decimal places. So 1, 2, 3 decimal places. Now don't just cut it off. Okay, that's called truncating it. And if you're taking AP Calc, that will be totally legal. But if you're not taking AP Calc, then you need to look at the next number over. And if it's 5 or less, then you're going to let it rest. If it's less than 5, you're going to let it rest. If it's more than 5 or equal to 5, then you're going to round it up. So this is a 1, it's obviously less than 5, so we're going to just keep it 0.707. That's to 3 decimal places. So here we go. Our solution here is going to be 0.707. And I like to use my little approximation equal sign so that we know that it's approximately this amount, that is not actually equal to that amount. And that's it, you guys. You know how to use your calculator to find trig. You know how not to use your calculator to find trig. And you know how to label all the sides of your triangle properly. I even taught you a little bit of Greek. I hope you have a wonderful rest of your day. Bye-bye now.